Let's do some more additional examples. Okay, so let's look at the set of even integers, right? Whether it forms a ring or not. So let's say R is equal to 2Z under addition and multiplication. Okay, and as usual, let's bring in our checklist and now let's take it one by one. Now, we know integers are closed under addition. So even numbers are also closed under addition. Right? If you have to actually show it, you will take two elements. A is equal to 2n1, B is equal to 2n2, where n1 and n2 belongs to the set of integers. And now A plus B should also belong to the ring R. So let's see 2n1 plus 2n2, which is nothing but 2n1 plus n2, which we can write it as 2n3, and we know n3 belongs to Z, right? So which means it is closed under addition. So closed under addition. Now associated, again we take two elements. A is equal to 2n1, B is equal to 2n2, where n1 and n2 belong to the set of integers. Okay, so A plus B plus C is equal to A plus B plus C. So let's take, and we require C also. So let C is equal to 2n3, where n3 belongs to integers. So 2n1 plus 2n2 plus 2n3 is equal to 2n1 plus 2n2 plus 2n3. 2 is common, so let's take it out. n2 plus 2n3, 2n1 plus 2 common out, n2 plus n3. 2 again is common, so n1 plus n2 plus n3. 2 again is common, n1 plus n2 plus n3. So therefore, it is associative under addition. Now additive identity, okay. 0 is the additive identity, and we know if we take A is equal to 2 and 1, then A plus 0 is equal to 0 plus A equal to A. So let's do the substitution. 2 and 1 plus 0 is equal to 0 plus 2 and 1. And we know this is going to be equal to 2 and 1. And 2 and 1 also belongs to R, right? So which means additive identity also exists. Now additive inverse, again there exists minus A, such that if A is equal to 2 and 1, where n1 belongs to the set of integers, then minus A is equal to minus 2 and 1, and adding these two should give us the identity, which is 0. So 2 and 1 plus minus 2 and 1 equal to 0. So this will give us 0. Okay. So additive inverse is there. Now addition is commutative. Let A is equal to 2 and 1 and B is equal to 2 and 2. So A plus B equal to B plus A. Now A is 2n1 plus 2n2 is equal to 2n2 plus 2n1. Now 2 is common, so 2n1 plus n2. 2 is common, n2 plus n1. And since n1 and n2 belong to Z, and we know integers are commutative, this can be written as 2n1 plus n2 equal to 2 times n1 plus n2 because the integers under addition are commutative. So addition is commutative. Now closed under multiplication. So okay. So if we have A is equal to 2 and 1, B is equal to 2 and 2, where n1 and n2 belongs to Z, A times B should also belong to R. So let's see, 2 and 1 times 2 and 2 is equal to 2 times 2 is 4 times n1 and 2. Now this can be written as 2 times 2 n1 and 2. Yes. So which means this is an even number and this is also an even number. So therefore belongs to R. So closed under multiplication. Associative under multiplication. So A is equal to 2 and 1, B is equal to 2 and 2, C is equal to 2 and 3, where N1, N2, N3 belong to Z. So 2 and 1 times 2 and 2 times 2 and 3 is equal to 2 and 1 times 2 and 2 times 2 and 3, which implies 4 and 1 into times 2 and 3, which is equal to 2 and 1 times 4 and 2 and 3, which implies 8. 8 can be written as 2 times 4 and 1 and 2 and 3. Again, we can write this as 4 and 1 and 2 and 3. So this is an integer and it is in that form. So this is associative. Now multiplicative identity. Now multiplicative identity is of integers is 1, but 1 does not exist, right, in R, or I should properly say 1 does not belong to R. So therefore no element exists such that, so no element exists such that A times 1 is equal to 1 times A is equal to A belonging to R. So multiplicative identity exists? No. Multiplication distributes over addition. Multiplication over addition. So for this, again, let's take 2 and 1. A is equal to B is equal to 2 and 2. C is equal to 2 and 3. So A times B plus C is equal to A times B plus A times C. And the other way around also we should do. This is left distribution. We should also show it for right distribution. But I'll restrict myself to left distribution. So 2 and 1 times 2 and 2 plus 2 and 3 is equal to 2 and 1 times 2 and 2 plus 2 and 1 times 2 and 3, which implies 2 and 1 times 2 is common and 2 plus and 3, 4n1 n2 plus 4n1 n3. Okay. So this becomes 4n1 times n2 plus n3, and this becomes 4n1 is common, so n2 plus n3. So both sides are equal, and we can write this as 2 times this quantity. So therefore multiplication is distributing over addition. So what is our conclusion? So therefore R is a RNG, that is a ring without multiplicative identity. As I mentioned in my previous session, if multiplicative identity does not exist, in many textbooks it's written as RNG and it is not treated as a ring. But in some other textbooks, multiplicative identity is not a must. So it is treated as a ring. So be clear about which one you are supposed to follow. Okay. So that was even numbers. Now let's look at an example with respect to matrices. So let us say we have a set of all matrices of the form 0, 0, A, B, where A, comma B belongs to the set of real numbers. Okay. Again, we bring in the checklist. Now, one, closed under addition. We can simply say, because matrices is a prerequisite for this part of our mathematics journey, we can just say matrices are closed under addition. So therefore, this is also closed under addition. But if we have to actually show it, let's say A is equal to 0, 0, A1, B1. B is equal to 0, 0, A2, B2. And we have to show that A plus B also belongs to R. So A plus B is equal to 0, 0, A1, B1 plus 0, 0, A2, B2. And we know this would be equal to 0, 0, A1 plus A2, B1 plus B2. You have to be very clear about why we are saying that this is also in the ring. Because A1, A2, B1, B2 belong to the set of real numbers. And we know in real numbers, the sum of any two real numbers belongs to real numbers. So therefore, this belongs to the ring R. So it is closed under addition. Okay. Associative under addition. So again, A equal to 0, 0, A1, B1, B is equal to 0, 0, A2, B2, and C is equal to 0, 0, A3, B3. Okay. And we have to show that A plus B plus C is equal to A plus B plus C. Okay, let's begin. 0, 0, A1, B1 plus 0, 0, A2, B2 plus 0, 0, A3, B3. You actually should write this instead of just watching it, because the more you actually physically practice it, you may understand it now, but later on when you try to do it, you may miss out on certain aspects. Okay. So now A plus B. So 0, 0, A1, B1 plus 0, 0, A2, B2 plus 0, 0, A3, B3. Now let's see. This implies 0, 0, A1, B1 plus, let's add up these two. So 0, 0, A2 plus A3, B2 plus B3 is equal to, let's add up these two, A1 plus A2, B1 plus B2 plus 0, 0, A3, B3. And if we add these two, we get 0, 0, A1 plus A2 plus A3, B1 plus B2 plus B3 is equal to 0, 0, A1 plus A2 plus A3, B1 plus B2 plus B3. So left hand side and right hand sides are equal, and A1 plus A2. Now A, B, C are real numbers. So sum of those real numbers is a real number. So therefore associative under addition. Now additive identity exists. That's the third point. So additive identity of a matrix is what? Zero of the appropriate order of the appropriate size is the additive identity. So let's see. This is 2 by 2 matrix. So 0, 0, 0, 0 is the identity, additive identity. How do we show this? Let A is equal to 0, 0, A1, B1. So A plus 0 is equal to 0 plus A is equal to A. So 0, 0, A1, B1 plus 0, 0, 0, 0 is equal to 0, 0, A1, B1. And this belongs to R. So additive identity exists. Now additive inverse exists. Existence of inverse. Now we know inverse exists, or more precisely additive inverse. So that is nothing but minus of the given matrix. So 0, 0, A, B, right? So if we take an element A is equal to 0, 0, A1, B1, minus A would be equal to minus 0, 0, A1, B1, or which can be written as 0, 0, minus A1 minus B1. So A plus minus A is equal to minus A plus A is equal to the additive identity. So let's take 0, 0, A1, B1 plus minus A is 0, 0, minus A1 minus B1 is equal to 0, 0, minus A1 minus B1 plus 0, 0, A1, B1. So this implies 0, 0, A1 minus A1 is 0, B1 minus B1 is 0. And this is again 0, minus A1 plus A1 is 0, 0, 0, which is nothing but the identity, or to be more precise, additive identity. Okay, so that means additive inverse exists. Now we have to show addition is commutative. So this is fifth one. Commutative. Addition is commutative. So again we require A1, B1. So let's say 0, 0, A1, B1 plus 0, 0, A2, B2 is equal to 0, 0, A2, B2 plus 0, 0, A1, B1, which implies 0, 0, A1 plus A2 and B1 plus B2 is equal to 0, 0, A2 plus A1, B2 plus B1. And since A1, A2, B1, B2 belong to real numbers, addition is commutative, right? Real number addition is commutative. So therefore, this is also in the form in which we require. So therefore, addition is commutative, in these set of matrices. So addition is commutative. Now we have to look at closure under multiplication. So let us say we have a matrix 0, 0 and A1, B1 times 0, 0, A2, B2. So this belongs to R. This belongs to R. We have to show that the result also belongs to R. So which implies, let's multiply it 0, A1, B2, 0, B1, B, and this also belongs to R because A1, A2, B1, B2 belong to R, the set of real numbers, which implies that A1, B2 and B1, B2 also belongs to the set of real numbers. So that means it is closed under multiplication. Okay, next is existence of multiplicative identity. So we know in case of matrices, I is the multiplicative identity, right? But the multiplicative identity I 2 by 2 is equal to 1, 0, 0, 1, right? But not in the form of the required matrix, that is 0, 0, A, B, right? So identity doesn't exist. So multiplicative identity does not exist. See, this is why you require this type of a checklist because I missed out associative under multiplication. So let's take up that. Okay, so let's say 0, 0, A1, B1 times 0, 0, A2, B2 times 0, 0, A3, B3. So whether we do it first this or we do the second two matrices first. Either way, it should give us the same result. Requires patience. A3, B3. So whether we do this first or this first, it should give us the same result. So let's see. Let's multiply 0, 0. Here it will give us A1, B2. And here it will give us B1, B2 times 0, 0, A3, B3 equal to, and here 0, 0, A1, B1 as it is times, let's multiply these two, we get 0, A2, B3, 0, B2, B3, which implies, now let's multiply these two, so we get A1, B2, B3. Here we get B1, B2, B3. And here what do we get? 0, 0, A1, B2, B3. And here we get B1, B2, B3. So they both are equal. So that means it is associative under multiplication. And we have already seen multiplicative identity doesn't exist. Now multiplication distributes over addition. So the ninth one. So let's take 0, 0, A1, B1 times 0, 0, A2, B2 plus 0, 0, A3, B3 should be equal to 0, 0, A1, B1 times 0, 0, A2, B2 plus 0, 0, A1, B1 times 0, 0, A3, B3. Okay, let's begin. So this as it is A1, B1 times, now let's add up these two. We get 0, A2 plus A3, 0, B2 plus B3. Okay, and now let's multiply 0, A1, B2, 0, B1, B2 plus 0, 0, A1, B3, B1, B3. Okay. Now let's multiply these two. 0, A1 times B2 plus B3. 0. And then we have B1 times B2 plus B3 is equal to, now let's add it up. We get A1 B2 plus A1 B3, then B1 B2 plus B1 B3, which implies 0, 0. We can just write this down, B2 plus B3, and B1 times B2 plus B3, and this becomes A1 is common, B2 plus B3, and B1 is common, so B2 plus B3. So both sides are equal. So which means that multiplication distributes over addition. So again, which means that is R a ring? R is a RNG, a ring without multiplicative identity, right? So again, depending on what your definition is, you can specify whether it is a ring or not. Okay, that is another problem looked at. I think that's enough for now. Bye.